Okay, so we're going to go through and look at all the different formulas and concepts and ideas that you need to know from Chapter 7, and there's a lot of them, so it's going to take a bit. So to start with, you need to know the special right triangles, and the way that we think about these, right, our first and easier of the two is the 45, 45, 90. We also consider it a isosceles right triangle. This is the one that we associate with the square root of 2. And so we say if our legs are a, then our hypotenuse is a square root of 2. We just multiply the side length by, or the leg by square root of 2 to get the hypotenuse, or divide by square root of 2, the hypotenuse by square root of 2 to get the leg. The other is the 30, 60, 90 triangles. And then on this one, we do it all based on the short leg. If we know the short leg, then we know the hypotenuse is 2 times the short leg, and we know the long leg is square root of 3 times the short leg. If we're given the hypotenuse, we divide by 2 to get the short leg, multiply by square root of 3 to get the long leg. And then, of course, we also never forget our old reliable Pythagorean theorem. Speaking of that, we also need to make sure we know the acute and obtuse versions of the Pythagorean theorem. If the two short sides squared, the sum of those two squares is greater than the third side squared, then that's going to be an acute triangle. And if it's less than, then it's going to be an obtuse triangle. And the easiest way to remember which is use the equilateral triangle as an example, and whichever one it satisfies, that's going to be the acute version. Okay, now into the areas. And most of what is going on in this chapter is area formulas. So looking at our area formulas, we're going to just start by talking about triangles. And we actually have 4 formulas about triangles that we need to know. The first is the most basic. Area equals 1/2 base times height. Remember, generally it looks like this, where here is your base, here is your height coming in at a perpendicular. But don't forget that there's always multiple ways to do it. So for example, we could have this be our base. And if that's the base, then the side length is extended, and that would be your height over here. And so in a triangle, there's always 3 different ways to get your base and your height, which is one of the ideas and concepts we have, which is writing the area of a triangle in 2 different ways. Okay, also remember that in a right triangle, the legs are the base and the height. Those are the base and the height in a right triangle. Then we had our Heron's formula. Remember, S is the semi-perimeter, and so it's S times S minus A, S minus B, S minus C. We had Shoelace Theorem. So if you're given I'm not going to go through this. You might need to look this up if you've forgotten it in your notes. But Shoelace Theorem is a way to find the area of a triangle if you know the coordinates of the vertices on a coordinate grid. And then finally, we had our special case, which is an equilateral triangle. And this is one, make sure you know this one. It will save you time. And the equilateral triangle is area equals side squared times the square root of 3 over 4. So those are the 4 that we need to know about triangles. That takes us then to quadrilaterals. So 4-sided figures. And so the first one we know is also shoelace, right? Shoelace can be used if we know for all the different kinds of polygons, if you know the vertices. But then we have parallelograms, and parallelograms include rectangles, it includes rhombuses, and then just basic parallelograms. And the area of a parallelogram is going to be 1/2 base times height. Remember, just like a triangle, it is, your base could be this and your height could be that, but at the same time, your base could be this side, and then your height would just be a line that is perpendicular, so something like this. to the other side. It's hard to draw in. And so there's always two ways in a parallelogram to find the area. And sometimes you know three of those four things, two of the heights and one of the sides, or two of the sides and one of the heights, and you can find the fourth one by setting the areas equal to each other. And this also used for a rhombus. If you got a rhombus, you certainly want to be thinking about that formula for a rhombus and a kite, but also be thinking about the area equals 1/2. It's not 1/2 base times height. It is base times height. Man, that was a bad mistake. So good to bring up. Remember, this is one of the ones that does not use 1/2. It's easy to mess that up, just like I did, and forget that, oh, wait a second. Triangle is 1/2 base times height. A parallelogram is just base times height. So a rhombus and a kite is a 1/2, and it's going to be area equals 1/2 times the diagonal 1 times diagonal 2. Find the two lengths of the diagonals, and that gives you, multiply those together times 1/2, and that gives you the formula. And remember, that works because of the perpendicular diagonals of a rhombus or a kite. Then don't forget that a square is a rhombus, and it is a parallelogram, but the difference is in the base and the height of a square are the same, so that's why we say it's side squared. And then also it's true that the diagonals are the same length, and so we could say 1/2 diagonal squared. And so the square is the simplest version of area for a parallelogram, or for a quadrilateral. And then the last one on quadrilaterals is the trapezoid. And so remember, this one does have a 1/2 in it. And so you're going to do area equals 1/2 the height times the sum of those two bases. Make sure it's just the bases you're finding the sum and not the two non-parallel sides. You need that for perimeter, but not for area. Okay, and then we've got our other polygons. And we have the one general. This works for every polygon, every regular polygon, as long as you know the two pieces of information. And this is the one that we're using a little bit now, and we'll use a lot later once we get to trig. And that is the one where it's the area equals 1/2 AP, where A is the apothem. Remember, apothem goes from the center of the regular polygon to half a side length, and then P is the perimeter. And so that one we didn't use as much, and so make sure you know that one. And then we had the regular hexagon. Remember, a regular hexagon is made up of 6 equilateral triangles, and so it's just multiplying that equilateral triangle formula by 6, and that simplifies to 3 side squared root 3 over 2. And then you've got your regular octagon. We had 2 of those. You've got the one that's given the side. That was area equals 2 side squared plus 2 side squared root 2. And then given radius, it was area equals 2 radius squared times the square root of 2. And then finally, we had some about the regular dodecagon. Remember that one given side length is the one where we partitioned the dodecagon into 6 squares going along every other side, putting a square off of it. And then what's left is 12 equilateral triangles. So it's going to be 6 squares, S times side squared, plus 12 equilateral triangles, which would be 12 side squared root 3 over 4, which simplifies just to 3 side squared root 3. So that's the area of a dodecagon given side length. And then given radius, it's going to be just 3r squared. And remember, that's the one, one way to kind of remember these is these start getting closer to pi r squared, right? 2 root 2 is around 2.8, 3r squared is just less than 3.14. And if you kept getting bigger and bigger versions of these, you'd get closer and closer to pi as your coefficient to that r squared term. All right, and then our last 2 things we learned about were arc length. Remember, when you're talking about an arc of a circle, we measure it in 2 ways. One is what fraction of the circle it is, and we do that in a degree, right? The measure of the arc is what is the degree associated with that arc, and that is what fraction out of 360 is that. And then the length would be if you actually measured it with a ruler. How long is that portion of the circle? And so the arc length is just going to be area equal, or the arc length equals, and then it's the measure of the arc. I'm just going to use AB over 360 times 2 pi r. And then we have the area of a sector. And remember, it's like the arc length formula, except that instead of taking a fraction of the actual circumference, you're taking a fraction of the area. It's usually a pi, so this is a sector. And so that's going to be the same thing, the measure of AB, the arc AB over 360. But this time you multiply by the area of a circle, pi r squared, instead of by 2 pi r, the circumference. It's what fraction of the area is that sector. Okay, so that gives you a really short or somewhat long overview of all the different possible formulas that come up on our Chapter 7 test.